time domain representation of linear time invariant systems. Okay, I hope you remember you had that in first year transistors, right? There is JFET or your BJT transistors. So every transistors can be characterized, amplifiers can be characterized by four things, right? Input impedance, output admittance, then what is that? Voltage gain and current gain, right? Or there are something like H parameters, right? Have you heard of H parameters? Or there is something called as beta. Okay. So whenever you purchase any transistor, okay, so this particular seller, he gives you the data sheet. Okay. The data sheet contains the H parameters, beta, right? Some of these factors. If at all you know them, okay, if at all you know those factors, you can predict the behavior of that particular transistor, how the transistor is going to give you the output, okay, when it goes in any kind of circuit, okay. So that means the H parameters, similarly for any circuit maybe, right, those ABCD parameters, right, they characterize that particular circuit and help you determine the output for various, large set of inputs. Similarly, the way we characterize any LTI systems, okay, the way we characterize any LTI systems is what we are going to study in this particular chapter. Okay, so specifically we are talking about the time domain representation of LTI systems. Again, in the frequency domain representation, there are 2 to 3 things that are of very much use to us. Okay. So there are 4 classifications, there are 4 ways a typical LTI system can be characterized in the time domain. Okay, there are 4 ways. Okay. So the first way is what we studied, right? The impulse response representation. If at all you happen to know the impulse response representation of an LTI system, that means if at all you happen to know H of n, the impulse response, or H of t, H of n is for discrete time, H of t is for continuous time. What can you do? If at all you know the impulse response, you can predict the output to different types of inputs by using the convolution operator, right? So that's a good thing, right? You just have to know the impulse response. If at all you purchase a system, if at all on the besides the box, if at all they has written the impulse response, then you can predict the output of that particular system to any kind of input, right? The vendor need not tell you for sign input, this is going to be there, for this input, this is going to be there. No, you just have to do it. Other than that, just by knowing the impulse response, you can also predict whether the system is going to be stable or not, whether the system is causal or not. Okay, so all those things also you can predict. Okay, so that is why this impulse response, so that is why we say just an impulse response can easily and in a efficient manner can characterize an LTI systems. What are the other characterizations by the other types of representation? This is the one which is there for us in the syllabus. We are going to learn it in detail. The second type of classification you might have studied in your PU onwards, right? It is using those differential equations. Remember the differential equations, of what use they are? Suppose I had a second order differential equation. You might remember the LCR circuit. Do you remember the LCR circuit? Okay, I hated the topic by the way. LCR circuit, inductance, capacitance, and resistance. Say I have a voltage source applied to this. Okay, say I have a voltage applied to this. Suppose these are my values R, L. Sorry. Okay. Say these are my values. Say there is an L, there is a C, and there is a R. If at all I apply the voltage here and I try to express it, so what sort of equation it will be? I will end up getting a differential equation. Remember? Yes, anybody? Do you remember this? If at all I apply voltage, Kirchhoff's law to this particular circuit, I end up getting a differential equation. What it will be? Will it be a first order or second order? Will it be a first order differential equation or second order?
First order.
First or second? If at all there is an inductance and a capacitance, it's going to be of second order. If there is only an inductance, then it will be of first order. If at all there is only one capacitance, then it will be of first order. 2 capacitors and 3 inductors, doesn't matter. All the capacitors can be represented as lumped capacitance. All the inductors can be represented as lumped inductance. Resistance, if at all there is a resistance only in the circuit, then it will be going to be zeroth order. Actually, the order of a differential equation indicates the number of memory elements. If the circuit contains only inductors, it is going to be first order differential equation. If it contains inductors and capacitors, assuming that all inductors can be represented as a single lumped inductance, all capacitors can be represented as single lumped capacitance. So a typical LCR circuit is going to be of give you a second order differential equation. Now tell me, given a circuit, you can extract the differential equation. Now, if at all I give you a differential equation, do you think that you can go to the circuit, you can design the circuit as well? Do you believe so? Are you getting the question? If at all I give you a circuit, an LCR circuit with certain inductance of this much Henry, capacitance of this much Farad, and resistance of this much so and so, you from there can get a differential equation, right? Now, similarly, if at all I give you a differential equation, from that, can you derive a circuit? Can you predict the circuit?
Yes,
Somebody?
sir.
Yes,
Yes, sir.
you can
We
predict
can.
the circuit, right? So that is why with impulse response representation, what we have studied just now, we have just began studying, you could predict the output of the system. You could predict whether it is stable or not. You could predict whether it is memoryless or not. You could predict whether it's causal or not, but you cannot predict the structure of the system properly, okay, and efficiently. With differential or difference equations, you can predict, okay, if at all you have the differential equation, you can always get this circuit for implementation in the laboratories, okay. Differentially in difference equation get you the circuit. It is also going to tell you the order. It is also going to tell you the order, and you might have studied in mathematics much frequent and more than twice maybe, that for different set of inputs, what are going to be the outputs, right? The solutions of differential equations, remember the topic. So that is why for a black box, a circuit, if at all you do not have the impulse response, but if at all a differential equation is given, still you can predict most of the properties of that particular system. You can even get the circuit of the system, and also you can efficiently reduce the components, maybe that also you can do. So the second type of representation of typical LTI systems, that too in time domain, is differential equation. Now that we are in signals and systems, okay, and there are discrete components, right? So in case of continuous time, there were inductors and capacitors, whereas whenever we are talking about discrete memories, the memory elements are now D flip-flops, and the corresponding equations in the discrete time are called as something called as difference equations. I hope you have not come across this term difference equations earlier, okay. So they are a discrete time counterparts of differential equation, okay. Something that we will study them as and when the time comes, okay. So this is the second type of classification that we have. The third classification that we have is a block diagram representation. LTI systems can be represented in terms of block diagrams also. So are you studying the block diagram representation in your control systems, by the way? Have you studied block diagram representation in your control systems? Block diagram reduction, yes or no? Representation, you can extract a circuit, you can get the transfer function and also the impulses from the block diagram representation. You can also efficiently reduce the number of components needed. You can efficiently reduce the number of multipliers needed. You can reduce the number of adders that are needed. So the topic that you study in your control system, simplification of block diagrams, so that some 13 blocks with 10 summing points and 5 multiplication points can be reduced to only 5 blocks with the 3 multiplications and 5 summing points, something like that. So a block diagram representation is also one more way in which time domain LTI systems can be represented in time domains. It helps you reduce the requirements, the hardware requirements, okay, and also predict the circuit. Then there is state variable representation, okay. So these you are going to study much detail in your control systems. Linear differential equations you have studied in larger detail in your mathematics already. there is a topic in your textbook. Let me see whether it is there in your syllabus or not. If it is not there in syllabus, we will not get much deeper into it. Okay. Now let us concentrate on the topic at hand. So impulse response representation. So why I came across this is while we studied about the convolution. So convolution could help us determine the output of any kind of system, given that only if you happen to know the impulse response h of n or h of t. Okay, if at all you don't know the impulse response, you cannot do all these things. Okay. Now let us continue with this introduction. Now let us continue to the topic at hand. Okay. So we studied the linear convolution by the way in the previous class. The topic is something like that. So here is a question once again. Say there is an LTI system with this particular impulse response, then determine the output of the system to this particular input. Now see the input here. What is this particular input? This is nothing but 2 into delta n plus 3 into delta n minus 1 minus 2 into delta n minus 2. Okay. When that is the case, what is the output that we are going to get, by the way? What is the output that we are going to get? See, the input is once again 2 into delta n. Okay. If at all I consider the individual inputs here, if my input is 2 into delta n, its output is going to be 2 into the impulse response, right? If delta n has a response h of n, 2 into delta n is going to have a response 2 into h of n. Okay. Okay. Similarly, if at all there is 3 into delta n, the output is going to be 3 into h of n. If delta n is shifted by 1 unit to the right, the impulse response will also be shifted to the 1 unit to the right. If delta n is scaled by factor minus 2, impulse response will also be scaled by factor minus 2. If delta n is shifted by factor 2, the impulse response will also be shifted by factor minus 2. Okay. And their outputs, by the way. Now, will somebody help me predict the output here? So 2 into h of n, what is that? What is h of n, by the way? 1 to 1, right? So I have 2 into h of n. Say 2 into h of n, 1 into 2. 1, 2, 1. Okay, into 2, right? I have to do into 2. Sorry. So what this will be? 2 into h of n. H of n is 1 to 1. 1 to 1 into 2. 2, 4, 2. Okay, let me have the arrow here. Let me have the arrow. Where? Arrow is here. Okay, see. This is the midpoint. Okay, see. At 0, it was 2. Okay, then you multiplied this with 2. This 4. This is the midpoint. Then 3 into h of n minus 1. That means now I have to shift by 1 unit. I will start from here. So here I have 3, 6, and 3. Okay. Then one more shift, minus 2 into h of n minus 2. So what do I have here? Again, I will shift minus 2, minus 4, and minus 2. Okay. So now I will add all the things. Okay. So I have a 2 here. Okay. Then 4 plus 3, 7. Then a 6. Then
6.
minus 1.
Minus 1. Minus 2.
Minus 2. Okay. I hope you might have done this exercise. Okay. Now see here. So I have this answer. So I know what is this. These are the shifts that you introduced. Okay. So this is just like your multiplication, right? In your notebooks, you have been doing multiplication from your 4th or standard, maybe, right? So something similar you do to in the multiplication also, right? You know what is multiplication, but the thing comes with certain rules. Remember, 1021, 1121 into 1121 into 42. The multiplication is the thing, but the rules, how do you do this, by the way? You multiply first with 2, then afterwards, right, you got something, then afterwards you write a plus here to indicate there is nothing here, then you do this particular, then afterwards you add. Okay. Something similar. This was a part of a single thing broken, whereas we got this particular thing. I guess every operator comes with certain rules, and here we are. Okay. So that was about the basic convolution. You got this particular method. So in the previous class, we were talking about the other method also. Remember, what is the other method, by the way? You write the first number here.
So some multiplying and addition. It was also similar. Yeah.
1 to 1 I will write on this particular side. And here I will write 2, 3 and minus 2. See, I will start from here 2, 3 and minus 2. Okay, then afterwards I will multiply this way or this way. How do I write it? How do I write it? See, 2, 3 and minus 2. Okay, this was the method I was talking about. Then you multiply 2, 4 and 2. See this. Okay, 2, 4 and 2. Then afterwards 3, 6 and 3. Then afterwards minus 2, minus 4. Then what is this one? What is this one? Somebody tell me. What is this one here?
Minus 2.
Minus
2.
minus 2.
Minus 2.
Thank God you are listening.
Minus
Okay. Huh? Now what we do? We draw these lines here. Okay. Draw this. Oh, wait. Huh. Now we draw these lines. Okay, like this, diagonal lines, and we add the values in those diagonals only. So what we get here is first value is 2, then afterwards 7, then afterwards
7.
6, then
6.
minus 1, then minus 2. Okay, then you can see starting point of this particular h of n is minus 1, right? See, coming from left side, it is starting at minus 1. Starting point of the first sequence is minus 1. What about starting point of the impulse response? This is 0. So my answer also starts from minus 1. If this is minus 1, I will put my arrow here maybe. Okay. So you can use any of the methods, but unfortunately you are not going to get these simple problems, right? They are introductory problems. Okay. So if at all you get, one is the graphical method, which you solved first 2 problems. Second is this particular method where you just multiply. Then this is also one more method. This is much easier method. But then you every now and then do not get these kind of closed form values where you can see h of n is also containing some 3 values. X of n is containing some 3 values. How often does that happen? Usually this kind of thing doesn't happen, right? Whenever I'm talking about a speech with you now, maybe my data is being sampled at a rate of I don't know, 16,000 samples per second. Okay, so there is no chance you are going to get this kind of limited width wavelength. So let us see a practical situation, how a typical inputs look like. Let us see how typical inputs look like. Here we are. Okay. Now somebody identify and tell me what is the problem with this question now. X of n is given, h of n is given, and we have been asked to determine y of n. What seems to be the problem? We have a method now. Can we apply the method here and try to get output? When I say y of n, if at all I substitute n equal to minus 3, I should be able to get the predict the value at minus 3. When n is equal to 49, I should be able to get the value at 49. I substitute n, I shall get the value there. Okay. Can I do that method? Can I apply the method for this particular case? Say he gives an alpha. Say alpha equal to 0.8. Suppose alpha is given to you. Can you determine the output? How easy or difficult the question is? What is the trick involved here? Can you solve it just by using the method that you studied already? Can we solve it using the method we studied already? Can we? Yeah, somebody. What do you say? Inas, Gnanish, Madhav. Somebody tell me, can I solve it? What is the problem here? Everybody just say hi, by the way. Everybody just type in a hi here. Okay. Many users are there. Just type in a hi for the attendance thing. Quickly. Everybody just type. Okay. Yes, now somebody tell me why this question is different from other questions. What is the trick with this particular question? What is the trick with this particular question?
Is it unit step function? U of n is unit step function, no?
U of n is
Unit step function.
Unit step. So when I multiply anything with U of n, I am telling that the signal is going to exist only on the right side. Okay, when I multiply anything with u of n, now you can see here, given the input x of n and h of n, he wants to get the output. See the question very carefully. See how author has mentioned that alpha is between 0 and 1. Because if at all alpha is greater than 1, then what's going to happen? We are going to end up getting a signal which is diverging, right? Going towards larger values as n. And this, when applied to a stable system, is going to give us unstable outputs. That is why author makes sure that he specifies that alpha is between 0 and 1, so that the input at least is stable. When alpha is less than 1, greater than 0 and less than 1, then we are going to get an input which is something like this. Did you get the catch here? You see, both the input and the impulse response here, both are of infinite durations. When they are of infinite duration, where even if the value of alpha is given, you cannot keep on calculating infinite values, right? In such case, we need a generalized expression for y of n, where if at all I simply substitute the value of y of n, I should be able to get the output. Okay, I should be able to get the output. Let us see what is the approach. So for these kind of things, you cannot solve the problem using the previous approach. The previous approach is only when there are limited number of values are given for input and the impulse response. Here, what shall we do? Let us draw the inputs, by the way. Okay, let me draw the input. Let us assume that alpha, by the way, sticks to this. So this is the envelope. Okay, this is the envelope, and here is my alpha to the power n. Okay. Okay. So can you listen to me? Somebody? Okay. Can you? Ihab, are you there? Can you listen to me? Inas, can you listen to me?
Yes, sir.
Okay.
I can.
So now alpha to the power n into u of n. Now see, when it is multiplied by u of n, I will simply draw the values on the right side. Okay. That's what u of n means. Okay. So something like this I will draw. A decaying exponential. The problem here is, as I told you, it is of infinite length. It decays and it is of infinite length. So this envelope, I would say, is alpha to the power n. H of n, by the way, is the impulse response. Unfortunately, my h of n is also is only on the right side, but still this also is having an infinite duration. Say this is also is having, so let me put the dots here, something like this, to indicate this is also going on the infinite duration. So how shall we solve problems like this? For this kind of problems, what we'll do, we'll stick to the formula. What was the formula of y of n, by the way? We studied that y of n is given by, what was that formula in the derivation what we saw? It was summation k going from minus infinity to infinity, x of k, h of n minus k, h of n minus k, n minus, this is the formula. Now I know what is x of n. Okay, I know what is x of n, but what is this x of k? What is this x of k? X of k is nothing but value of x of n at k equal to 1, at k equal to 2. When I say x of n, it means all the values of k from minus infinity to infinity. When I say x of k, I am talking about a particular value, x of 0, x of 1, x of 2, x of 3, and so and so. Whereas h of n minus k, now what I will do is, for the convenience, see here, see this step very carefully. I will call this thing as, this I will call it as x of k. Okay, this I will call it as x of k. Whenever all the k I consider from minus infinity to infinity, so this x of k becomes x of n only. Okay. So for different values of k, I have alpha to the power k. Okay. So similarly, this I will call it as y of k. This also I will call it as y of k. So I'll call it as y of k. Both of them are starting from 0. Both of them are starting from 0. Now what I will do is, let us go by the formula. Okay. Now what I have to do is, for y, if at all I want to know y of 0, what should I do? If at all I want to know y of 0, I should do k here. Wait a second. Okay. K here goes from k here. I should consider all the values from minus infinity to plus infinity. Okay. That is the meaning here. Okay. So I should consider k from minus infinity to plus infinity. All the values that are there into contention. When I say y of 0, what should I consider? X of k, h of 0 minus k. When I say y of 1, h of k, x of k, h of 1 minus k, y of 2, h of k, y of 2 minus k, and so and so. So we cannot do these things, right? Let us generalize. So for generalization, let h of k, there it is, there be h of k. What I will do? First I will draw. Wait a second. I have written this as y, right? Okay. Wait a second. This is h. Okay. This is h of k. What I will do to begin with, I earlier told you, see, there is h of k. If at all I want to do h of n minus k, you can see this is h of minus k plus n. Remember, this is h of k. This is h of k. Suppose I want to do h of n minus k. This is equivalent to minus k plus n, right? Right. So what did I tell you in the first chapter? Shift first and then scale. Here what I will do, I only contradict. This is by hiking, okay? So what I will do is, first I will scale, then I will shift. See, the method is first you have to shift, then you have to scale. But if at all I want to scale first and then shift, I should do it ulta. So what I will do is, let me draw h of minus k first. I will draw h of minus k here, okay? So which I would call it as h of n minus k only. But let me say for the timing that n is equal to 0. Okay. Let me say for the timing that n is equal to 0. So this is h of minus k. So if this is h of k, h of minus k, how does it look like? Somebody tell me, h of minus k, how does it look like? All the values at 0,
Will be
1, 2,
shifted towards the left
yes,
side.
we are going to have the mirror image. So it's now going to start from minus infinity and it will end at 0. Okay. See, this is a discrete time signal. The upper envelope is only for my convenience. Okay. This is a discrete time signal. So I should be drawing these bubbles here. Okay. Now this is h of n minus k. Now see the formula for convolution here. What is the formula for convolution? Y of n equal to x of k, which we have multiplied by h of n minus k. Now what I have to do is, I should go on shifting. See here, I should go on shifting from minus infinity to infinity. Now I want y of 0. I say I want y of 0. I should keep n is equal to 0. If at all I say n is equal to 1, now what is the usual case? N minus 1, when I say, I should move to the right side. When I say plus 1, I should move to the left side. But since what I have done here, instead of doing shift first and then scale, I have scaled first, right? Now that's going to be ulta. So that is why for the cases when n less than 0, okay, now see here what I want. I want an expression, generalized expression for y of n for all the values of n. I want to know the value at n equal to 21, n equal to minus 19, n equal to minus 10, n equal to minus 3, n equal to 0, n equal to 1, n equal to 2, n equal to 21, n equal to 43. So for negative values of n, what shall I consider? Let me start drawing this particular thing. Y of n minus k, say for n less than this, suppose n equal to say minus 1, say n equal to minus 3. Then what I will do is, this will look something like this. For say n equal to minus 3, it is going to look something like this. Okay. It's going to start from minus infinity and it is going to end at minus 3. Are you following? Are you following, everybody? Whatever I have drawn here is h of minus 3 minus k. Okay. And for a change, what you studied in the first chapter, I have done the scaling first. That is why when I said n equal to -3, instead of shifting it to the right side, I have taken it from the left side. Okay. Now let us multiply. What is the formula? What's going to be y of n now? What is y of n? Y of n is h of k multiplied by h of n minus k. Now let us start the multiplication. Let us say at n equal to -5, say this is -3, say this is -4, say this is -5. Now at n equal to -5, okay, what is the value of x of k? Somebody tell me. At n equal to -5, what is the value of h of n minus k? Somebody, I'm waiting for an answer. Waiting for an answer. Tell me. Let all I multiply. Say at -6, what is the value of h of n minus k? This is h of n minus k. Okay. This figure is h of n minus k. What is h of n minus k here at -6? What is the value at -6? Yeah, what is the value at -6?
Will be 1.
1. What is the value of x of k at -6? Can you guess? What is the value of x of k at -6? Do you see anything here on this left side? Do you see anything on the left side? What is the value of x of k at -6? Somebody. Roshan, Nutan, Shreya, Madhav, Naneshwar. What is the value of x of k at -6? We have. Okay. So what we'll do, I will send you a link. Okay. It's time. I will send you one more link. Okay. You can join in there. Just join. We'll wrap it up in 10 minutes.